So we're going to do lesson 2 today in topic 3, and your notes start on page 53. So if you want to turn to page 53, you might also want to have your, it's going to be a little hard to do. The other option instead of watching this video is you can just go through the interactive student edition, and you can find that in Schoology, and just step through that, and that might be faster and easier. I'll let you decide. So the first thing you're going to be doing is you're going to just listen to this flowchart. Just go through and do this. Pick any numbers. Try the puzzle with 6 different integers, any kind, and just record your answers here in the table, okay? Then make a prediction about what the final number will be for any of the numbers. Explain. And then if you want to predict what would happen, well, I can't get that, but would your prediction be true for all numbers? So just think about that, and I'll let you do that. It's kind of an interesting thing, and I just want you to think through it, so I'm not going to do it for you. Okay? So what we're going to look at first is how can you represent a function rule. So let's look at what a function rule, and I've kind of talked about this before anyway. A function is just a machine, okay? So if we think of a function as a machine, and if you were in class, we talked about the pasta machine. You put the pasta dough in, and then you get the pasta out, okay? So this machine, though, is we're going to put x in. So we're going to put x in the machine, and the machine is going to do 5x plus 1. And when we get done, we're going to get what the function is equal to. So f of x is read, so this f parentheses, x parentheses is read f of x. So this is read f of x, okay? This is function notation right here. And what function notation is, it's a method of writing variables as a function of other variables. The variable y becomes a function of x. So in other words, f of x is y is going to change into f of x. So wherever we saw y, when we got y by itself, so if we got an equation in slope-intercept form, so y is equal to 5x plus 1. The only difference is that now, instead of y, we're going to use f of x. Okay? But we have to get, with a function, what you have to realize is it is just like slope-intercept. You have to get everything on one side and the y on the other side. Okay? And the reason this is so awesome is because then we can just talk about each function. And the functions are going to have different names. F of x is the most common, but you'll also see g of x, h of x, and so forth. Okay? The function f is defined in function notation. So this is function notation when I use f of x. So it says find the value of g of x. So now they're just using the function g. Does it make any difference? No. And one of the misconceptions is people think that this is g times x. It is not. This is g of x, okay? So all we're going to do, you can probably guess, what do you think we're going to do with that 3? Yep, we're going to plug it in here. And the way we write it is that we write g of 3. So what is the function? What is the function doing at 3? So when x is 3, what is our function doing? So we just go g of 3, and in place of x, see how I have an x right here? I had an x, so this was g of x. So I had an x right here. So in place of x, I'm going to put in 3. So I'm going to put in the number 3 right here. So this is g of x. Bad handwriting. Let me correct that. This is g of x, okay? And this is equal to, well, 5 times 3 is 15, plus 1 is 16. So we can say g of 3 is equal to 16. So the function g at 3, when x is equal to 3, is 16. So we could also say that y is 16. But this is how we would do it in function notation. Now you're going to evaluate. So evaluate, look at that root word. Find the value of, this means to find the value of, okay, the function. So evaluate the function when x equals to 4. I think you know what to do here, right? Try it. Go. Did you find out that g of 4, you plugged in 4, wherever you saw x, and then you just simplified it using your order of operations? I'm going to multiply first and subtract, and I get negative 11. Good. Do B. Go. So h of x is equal to 7x plus 15. And they're saying that x is equal to 4. So I'm going to find h of 4. So what that means is any place where I see x, I'm going to put in a 4. So that's 28 plus 15. So h of 4 is equal to adding 43. So h of 4 is 43. That's what the function is doing when x is 4. That's what the function is at. And this is our machine. We're putting it into our machine. We're plugging the 4 right in. Okay, so this is our machine, and we're plugging the 4 right in and see what we get on the other side. Okay, so this one you do not have in your book. It is in the interactive book. So if you want to see this problem, it's in the book. And remember, you can always just watch and see what the solution does, okay? The cost to make 4 bracelets is shown in the table. How can you determine the cost to make any number of bracelets? So for 1 bracelet, it costs $17. 2 bracelets, $32. 3 bracelets, $47. 4 bracelets, $62, right? So if we could just write this as an equation, what do you think these are? These are ordered pairs, and this is going to act like your x, and this is going to act like your y, right? So what I could do, and I'm going to tell you straightforward, there is one easy way to do it, is that you can just take and treat these all as x and y values, and you could just pick 2 points and go, I'm going to take this point and this point, I'm going to subtract and find slope, I'm going to plug it in and find the y-intercept, okay? So that is one way you can do it, and so what I'm saying is that you can come over here, because I'm going to show you another way to do it that's really awesome, okay? I can come over and find slope, so I take 32 minus 17 and 2 minus 1, and I get a number. Let's see, that'd be 32 minus 17. I get 15. That's my slope. I can plug it into point slope or slope intercept. So point slope, y minus y sub 1. I'm, of course, going to use 1 and 17 is equal to 15 times x minus x minus 1, my x value. So y minus 17 is equal to 15x. 15 adds 15 to both sides. Y is equal to 15x plus 2. Okay, that's the equation. Now, I'm in function notation, so I would write it in function notation. F of x is equal to 15x plus 2. So that would be my function. Okay, now there is another way to do this using the table, and I want to show this to you because it sometimes kind of shows up in our EOC test, and so it's kind of helpful to see. So what we're happening is, remember I told you that this is x and this is y. So if I could just find out, what is it changing by? Is it changing by the same thing every time? So take 32 minus 17. What'd you get? You got 15, didn't you? And 47 minus 32 is 15. And we're adding 15 every time. Okay? Now what's happening from here to here? Oh, I'm adding 1. And I'm adding 1. And I'm adding 1. So what is my change in y? It's 15. What is my change in x? 1. So my slope would be equal to 15. Now, there's more to it. This is really cool. So far I have my equation is going to be 15x. But we have to find this y-intercept. So I could plug it in right now, okay? But here's the other thing I can do. See how it goes up by 1? And remember that your y-intercept, this right here is your y-intercept. My y-intercept, my x value is always 0. Right? So see how I went up by 1 every time? If I go down by 1, what do I get to? 0. And if I go, so I went down one place on my chart here. If I go down one place on my chart here, I would actually take 17 minus 15, and I would get 2. So that is my y-intercept because this is the point 0, 2. So this would be a 2. And I would say f of x, I'm going to clean that up a little. So my function, instead of a y, I'm going to use a function, 15x plus 2. Kind of cool, isn't it? Okay, good. So now you get to try. Let's see. I'm going to try the method that I just showed you, but remember the fallback is you can always just pick 2 points, find the slope, plug it into point slope, and go with that. So this is going up by 1 every time. Yay. That's nice. That's going to go up by 1 every time. And then what does this go up by every time? So take your calculator. What's 13 minus 6.5? Is that 6.5? Okay, take 19.5 minus 13. Yay, I get 6.5. And guess what I'm going to get here? Let's just be sure, though. And we get 6.5. Now, this should look familiar because you did something like this with the constant proportionality in 7th grade. So what's my slope? It's 6.5 over 1, okay? Because it's just changing by 1. So that's my slope. So f of x is equal to the slope times x plus, let's see what our y-intercept would be. So what I can do for my y-intercept is instead of going up 1, I'm going to go down 1. That gets me to 0. So then this value right here would be my y-intercept. So here I was going up by 6.5. Now I'm going to go down by 6.5. And what do I get to? I get to 0. That's my entire function. And I would just write it as f of x is equal to 6.5x. Pretty cool, isn't it? Okay, I'm going to let you try B. Go ahead and try B. Okay, and then we'll be back and talk some more. So hopefully you figured out that your slope will be 3, be 3 over 1. So that's my slope. So far I have f of x is equal to 3x. Now, go try and find the y-intercept. Okay, do it just like what we did over here on the first one. Try to find that y-intercept. Go. So here I went up by 1. So now I'm going to go down by 1. And when I go down by 1, I get to 0. So that means whatever this number is going to be my y-intercept. Here I went up by 3. Now I'm going to go down by 3. So 1 minus 3 would be a negative 2. That's my y-intercept. So you can leave it like that, or you can write it as f of x is equal to 3x minus 2. So we can now find the function and what that would be. And you would see that if this is my function, I could take my x values, plug it in, and I would get my y values. Good. So Tamika records the outside temperature at 6 a.m. And whenever you see this symbol right here, see that symbol? That means that it's going to be in your student interactive book, and it's not going to be in your book. So if you want to see this problem, now right now you're seeing it, so it's not a problem, but you could find this in your book. So at 6 a.m. records the temperature. It's -3 at 6 a.m. Okay? The temperature increases by 2 degrees Fahrenheit every hour for the next 6 hours. If the temperature continues to increase at this steady rate, so that's your slope, what will the temperature be at 2 p.m.? So first we're going to write a function for that. So we have f of x. Okay, now what's happening? How is it changing? Well, every hour it's going up by 2, right? So that's going to be 2x. Well, where did it start at? Where did it start at? What was the temperature? Right, -3. So this is my starting point because that's where they said they originally took the temperature. Okay, so now it's going to increase every hour for the next 6 hours. Okay, and that's where they got the 2 o'clock. No. Okay, so it says for the next 6 hours. Now that would just take it, if I go from 6 a.m., 6 hours would be 12. But it says if it continues, what would it be? What would my temperature be? And that would be my equation, okay? So now what we're going to do is we're going to say, well, what would 2 p.m. be? What time would that? So let's count. We're going to go from 6 a.m. and we're going to go to 2 p.m. So 6, 7, 8, 9, 10, 11, 12. There's 6 fingers. And then 2 more, so 8 hours. So we want to find f of 8. Yes? So I'm going to find f of 8 by taking 8 and plugging it in for x. So that'd be 16 minus 3. Our temperature would be at 13 degrees Fahrenheit. Okay? Now I want you to notice it talks about hours and every hour and that rate, and that's going to make a difference on this next one. So the B part of this in the book wants to know if it's realistic. That does the linear function realistically represent the temperature for the domain from 0 to 24? So they're saying 24 hours in a day. Is it realistic to be able to use that function that we were just looking at to see it? What do you think? Hopefully you said no, it's not realistic because of the sun. So we know that our temperature starts at a lower temperature. Then when the sun goes up, it's going to go up higher, and then it's going to come back down because the sun goes down. So we can't realistically use that function that we just saw because as the sun comes up, and if it's a sunny day, your temperature is going to go up faster than if it's a cloudy day or at night. Okay, so it's not realistic, but at least shows us what we could do. So if we wanted to graph this function, we could just plug in points. So this says drag the points. That's because it's assuming that you're in the interactive book. And you're going to sketch this. Well, look at this. Doesn't this look familiar? Does it look like slope y-intercept? So what's my slope? -1. What's my y-intercept? 1. So we can just graph these. Functions can kind of be written in slope-intercept form. They a lot of times are. So we can just plot it. So my slope my y-intercept is 1. I'm going to go down 1 and over 1, up 1 and over 1. And there's my graph. Yes? Good. Hopefully you remember it since it was just last week. You try the next one. Try it, please. And even if you just have to sketch it in your book. Okay, I never remember if they're going to give you grids or not. Okay, so my y-intercept is 1. My slope is 3 over 1. So I'm going to go up 3 over 1. And I can go down 3 and over 1. And there's my graph. Okay, good. Okay, so a chairlift starts at a half mile above the base of a mountain and travels up the mountain at a constant speed. How far from the base of the mountain is the chairlift after 10 minutes? Okay, so it starts at 0.5 miles. You know what that's going to be. That's right, that's going to be your y-intercept. Okay, now this one creates a couple things. One, notice that it says that after 10 minutes, where is it? But look what it rates it here. It's 6 miles per hour. So this one is in hours and this one is in minutes. We can't be in different units. So what we're going to do is we're going to do just a little, what's called unit analysis. So we start off at 6 miles per hour. Okay, and that says the word hour. Now we have to have it end up in hours because that's what this is talking about. So we're going to have to convert the minutes. Okay, so we want to end up in miles per minute, right? Because we want to find out how much it is in minutes. So what we do is that we're going to now convert this using our unit analysis. And this is something that's used in science all the time. See how it's 6 miles per hour? So I want to get rid of the hours. So that means I'm going to have to cancel those out, kind of like you do with fractions. And now, if I have 1 hour, how many minutes in that? That's 60 minutes, right? Do you see what I did there? So this is my conversion rate right here, 1 hour per 60 minutes. I could always flip those depending on what I had. And the reason this works is because I can cancel out my hours, and then I'm going to have miles per minute. And then I just have 6 miles per 60 minutes. And I reduce that down to be 1/10. So it's 1/10 mile per minute. Okay, so this is unit analysis, right? What we're doing right here. And we just kind of set it up so we can cancel out whatever we don't want it to be in. We wanted it in miles per minute, so we had to convert that. Okay, so that is going to be our rate of change. And this is what it starts out. So our equation, f of x is equal to 1/10. Remember, that's just 0.1. So 0.1 times x plus 0.05 miles. Oh, hold on a second. I just had to check something for a second because I wanted to make sure this was in miles right here. So this is miles per minute. So that is accurate because that's in miles per minute. And this is in miles. So you wouldn't have that 0.5. Whoops. You'd have 0.05. Okay, and there's your function. How far down the base of the mountain is the chairlift after 10 minutes? And that's the reason we had to change it into minutes, and so we could just take this 10 and plug it in. So we're going to find f of 10. So take f of 10, and we're going to plug in wherever see x, we're going to put a 10. Okay, so 10 times 0.1 is going to be 1, and 1 plus 0.5 is going to be 1.5 miles. So we know that it's 1.5 miles after 10 minutes. Okay, whoops, and I'm just hitting all kinds of things wrong here after 10 minutes. But another thing we need to pay attention to is that it says that it takes 15 minutes to get up to the top. If I'm talking about minutes, that is going to be my domain. So let's look at our domain here for a second. Our domain would go from 0 minutes to 15 minutes. Now, we only wanted to find out what would happen at 10 minutes. But if we wanted to look at our domain, it goes from 0 to 15 because we're then at the top. And the way that we would write that in set notation is that we would say, we'd make a set bracket, x, such that 0 is less than or equal to x, which is less than or equal to 15. That's what our set notation would look like. Okay, now the other thing is we need to realize, where are we at 15 minutes? It says that we're at the top, so let's find out what that top would be. So that means that we would take and plug 15 minutes in. So if I plug in 15, I would find out what is the distance up to the top. So I'm going to say 0.1 times 15 plus 0.5. And I get 0.1 times 15 plus 0.5, and I'm going to get 2. So to get all the way up to the top, it's going to be 2 miles. Okay? And that's going to make a difference. So here's our domain if I am traveling at a rate of 6 miles per hour. Okay? Keep that in mind for the next problem. Okay. So, a chairlift starts at 5.5 miles above the base of the mountains. This is the same problem, but instead of the constant speed of 6 miles per hour, we want to find out what happens at 4 miles per hour. So how is that going to change the function? How is that going to change the graph? How is that going to change the equation? And it also wants to know, what is the effect on the domain? So let's take care of that. So 4 miles per hour. So we're going to have 4 miles per 1 hour. And we're going to convert that. So the way we do it is we have to get rid of hours. So we have to be able to cancel those out. And we want to end up with per minute. So remember, we want miles per minute at the end. Okay? So how many hours per minute? Nope, 1 hour per 60 minutes. So my hours will cancel out. So that's the reason I know I did it right. And then I'm going to get 4 miles per 60 minutes. So that's going to reduce down to 1/15 miles per minute. I kind of left a lot of space there, but that's 1/15 miles per minute. That's going to be our slope. So our new equation, our new function, is going to be f of x is equal to 1/15 x plus 0.5. Okay, so let's look at our domain. Well, in order to know our domain, we have to be able to figure out what is the top of the mountain. So we know we're still going to start at 0. And we know that the top of the mountain is at 2. Okay, that's going to be when we're all done is at 2. So we're going to find out how much time does that take. In order to find out our domain, remember, is our minutes. So we have to find out our total minutes. So we know that the distance up the mountain is 2. We found that out on the last problem. So we're going to take 2 is equal to 15x plus 0.5. Okay, and so we're going to just solve for x. So I'm going to subtract 0.5, and I get 1.5 is equal to 1/15 x. And I'm going to clear that fraction by multiplying through by 15. Okay, and we find out that x is equal to 22.5. I'm going to double check that, make sure I did it right. And I get 22.5. So that is our total amount of time that we're going to be up that. So that means that our domain is going to be x such that 0 is less than or equal to x, which is less than or equal to 22.5. So how does that affect our graph? That means it's not going up as fast. So our graph, this second one, this miles per hour, would not be as steep as the 6 miles per hour. Okay, and you might remember that from constant proportionality, because the bigger the constant proportionality, the steeper the line. Great. So how can I identify a linear function? F of x, okay, or g of x. That's going to be a linear function. To make it linear, I'm going to have a power of no bigger than 1. Highest power is 1. Give a real-world example of a function that is linear and one is not linear. I'll let you come up with that one. Read it in the book. Check your answer. Go to that interactive and find out what it says. What is the difference between a linear function and a linear equation? Hey, that's a good one to read about. Go to your interactive textbook and read about that one. The cost of using a game facility is $1 for every 12 minutes. Talia writes the function as a cost per hour. So we have to convert this to the cost per hour. So if we're talking about the cost per hour, we have to set it up that first off, it's $1 per 12 minutes. And then we have to realize we're going to have to multiply it by something. We want to come up with the cost per hour. Okay? So we have to get rid of minutes and we have to change it to an hour. We want the cost to stay the same. So if I want to get rid of minutes, I'm going to put minutes up here. And I want it in hours, so I'm going to put hours down here. Well, what do I know about minutes and hours? I know there's 60 minutes in 1 hour. So what's going to happen here, using my unit analysis, I can cancel out my minutes. I'm going to multiply across and I get 60 over 12. So that's going to give me $5 per hour. Okay, so this should have been a 5 because we had to convert it. Okay, so this one wants you to find f of 2 and it wants you to find f of 6. So what you're going to do is you're going to plug 2 in, right? You get 8 minus 3, so f of 2 is equal to 5. You do the other one, go. Did you find out that f of 6 was equal to 21? Yay! So now your next problem, you're going to find f of 2 again. So you're going to plug that in. Now this is a great order of operations. That's a negative out in front. So 2 minus 2 is 0. So it doesn't really matter. F of 2 is equal to 0. That negative didn't affect it. Try it when you plug in the 6 and see what happens. Go. Did you get that f of 6 was equal to negative 4? Nice job. Okay. So now, what is the last one? Number 8. What function models the height of the periscope lens at time t? So we have our rate. We have our beginning, okay? So we're going to find out what we can do with this, and we're going to get f of x is equal to our rate plus our beginning height, okay? So that's our function. That's what they're asking for. If the periscope reaches its maximum height after ascending for 22 seconds, okay, so remember this is inches per second. So we're going to find f of 22. 6 times 22. Why can't I do this? That gives me 6 times 22. Which is 132 plus 24, which is equal to 156 inches, okay? That's after 22 seconds, in 22 seconds. But it says it wants to know the height in feet. So if I have 156 inches, I want to get rid of inches, and I want feet. So that means I'm going to cancel out my inch. Oh, wait, put it in there first. So I have 12 inches per 1 foot. So I have to put it diagonally like this so my inches cancel. Then I multiply across, or I can just divide. 156 over 12 gives me 13. So 13 feet. They wanted it in feet. Okay, great. So work on the homework now. If you have questions, you know where to find us. Thank you.